So hello everyone, my name is Paul Pop. I'm a professor at the Technical University of Denmark. I was a PhD student like you. I got my PhD at Linköping University, not far from here. I was also attending summer schools. I think that's great when you are a PhD student. My first summer school was going to Copenhagen, and that's where I ended up then as an associate professor. So these are also very good ways to build your network. And it's the same person that organized that summer school that later recruited me to become an associate professor. So I think that's a nice part of a summer school and get to know each other and speakers and so on. So right now I'm a professor at the Technical University of Denmark. I'm also coordinating something which is called the Nordic University Hub on Industrial IoT that is co-sponsoring this school. So I'm happy that we can support bringing great speakers here. And I'm a computer scientist, so my research is on algorithms. I especially look at how to develop optimization algorithms that help you support you in designing complex cyber-physical systems. So this you don't have to read everything. This is an overview slide basically telling you what is my research about. It's about doing methods and implement it via software tools to do all sorts of systems engineering aspects related to cyber-physical systems. And for example, here the contributions are defining new optimization problems. And then these are the typical venues where I publish, just so you know my background. But, and also doing analysis, especially timing analysis, and this is in collaboration with companies and in EU projects, national projects, and so on. While doing this research, I was exposed to, let's say, the trends that are happening currently in cyber-physical systems architectures. And this is what I'm going to report. Because you have to know, understand what is a cyber-physical system, know its architectures if you want to support designers in developing such architectures or using them to implement functions. So this is what I'm going to talk about. And I heard that in the past few days you have already covered some issues related to safety assurance and certification. I will not talk about that. I will actually focus on the evolution of cyber-physical architectures and what are the trends. And there are two huge mega trends. One of them is called more. I'll talk about that, talk about multicores and deterministic networking and something called fog computing. And I'll talk about something called more than Moore if I have time, let's see, because I'm staying in between, so lunch is coming after my talk. And of course I'm reusing some slides from various people, so I just wanted to mention that. So there are two mega trends. One I would call more Moore, and everybody has heard about Moore's law, which is not really a physical law, but it's basically telling you that you can get smaller and smaller transistors, you have cheaper microprocessors and all that. Maybe it's becoming more difficult to make them smaller, but you still can put a lot of them because now you have multi-cores and so on. There is another trend, and I really like to visualize it like this because if you see the linear curve that is actually exponential but is typically showed on an exponential slide, you don't realize that something that was so big 10 years ago, now it's something here. So you can really squeeze it. That's the basis of the microelectronics revolution. But there's something else there, not only more Moore, but also something called more than Moore. There is other things not related to microelectronics and semiconductors that are integrated with current cyber-physical systems architectures, which is analog sensors and also things like BioChips, and I'm going to mention that if I have time at the end. So I guess you have been exposed now in the past few days about these definitions of cyber-physical systems and also discussed that many of these systems that are autonomous are safety critical. They may endanger human life or the environment. Often these are also real-time in the sense that their functionality depends not only on the correctness of the computations but also at what times these are delivered. They may have deadlines. If you miss the deadlines, that's a failure. And they are becoming networked, for example, and forming systems of systems. And they are connected to each other and to the cloud and the fog and so on. We'll have such cyber-physical systems maybe more than 50 billion more than humans on the planet anyway already now, and probably half of them are safety critical in real time. And there are a few drivers in terms of architectures. One big driver is that we move from products to systems of systems. So if before, for example, you had one product, it could be a tractor. Nowadays is no longer a tractor. A tractor, maybe you get some data about it, becomes a smart product, then it becomes a smart connected product when you can see it on your laptop. It's connected maybe to a harvester or other things, and then it's connected to the cloud. So you have a system of products and then systems of systems. And these may unlock a lot of value, and these are some of the questions that researchers are looking at when you have such systems. And these are also influencing the type of architectures you need for them. Especially if you want to keep them safe. Then of course you have heard about autonomous systems. It's not only about vehicles, a lot of other things are autonomous, and not only robots. For example, this is the Copenhagen Metro, which is autonomous. These are autonomous tractors and harvesters that work on a field. You have autonomous mining operations, for example. These huge trucks, there's no driver in the truck, and they are going around, just for comparison, a person, and this is the wheel. And of course, hopefully, and this would also unlock a lot of value in the, let's say, global GDP going forward. But of course, it's difficult to make sure that you keep them safe, and then the question is, what are the hazards, what is the right practice to assure them, what are the right barriers, and so on. Another mega trend is that, another driver, sorry, is that we're moving towards something called Industry 4.0, where we are replacing the current operations technology, it's called, that is hardware and software dedicated to control physical processes in a manufacturing plant. So basically, the way the robots are controlled is changing. A lot of people want to bring that functionality to the cloud, and in the future, it will be implemented by networked cyber-physical systems. And a lot of functionality will move and be virtualized. So your PLCs, programmable logic controllers, and robot controllers will become software running somewhere in the cloud or something called fog, which I'll mention in a moment. So these are some of the drivers. And then what about the architectures? First of all, architectures are distributed. And there are several reasons why they are distributed. So you have networks inside a car, you have networks inside a plane, inside everything, railway and so on. Maybe even inside a robot, you'll have some devices connected. Often it's some physical reasons, because you have to be closer to sensors and actuators, but it's also about dependability. If a part of a system fails, you don't want the whole system to fail, so you want to contain the failures. It's also about putting more systems together, especially in vehicles. An integrator, like, for example, the known companies, let's take also not only cars, but also other type of vehicles like trucks. So Volvo Trucks will not develop all the electronic control units, ECUs inside a car, but will buy from different suppliers, and this is possible then to compose it, the different subsystems in a distributed architecture. You can scale it, you can add more nodes to it, and so on. It's also about maintaining it in terms of cabling, modularity. You can swap an ECU that is broken, and so on. So you have distributed computers interconnected in networks. And I give you some examples now. From Avionics, this is what currently what the picture is. This is in an aircraft, Airbus 380. And you have several computers connected to each other. Let's talk about connectivity. Initially, you had dedicated wiring, and you had hundreds of kilometers of cables going around in an airplane. Nowadays, this is replaced with things like AFDX, which is an extension of Ethernet to make it more dependable and time predictable. But still, you design individually each computer for the airplane and for the function. So you would have, this would be a computer, and they would sit in a cabinet, and they would be physically separated, connected via different networks, which are redundant, and so on. And if you fly an airplane, you're using all technologies, because that's the only technologies we know exactly how they fail. It's the only way to have, let's say, safe operation. For a flight control system, I don't know about Airbus 380, but in 340, 330, when you are flying, it's an 8286 processor and an 186 processor. So it's 5 processors, but they are very old, and they are not even programmed with the C compiler. They are programmed in assembly languages and something called PLM, I think. It's mostly because probably at that time they did not have what is called a qualified compiler. They could not trust that the assembly language coming out of the compiler would actually be correct. So this is, let's say, the current state in avionics. In vehicles is more advanced because, let's say, the perception of risk in society is that risk is smaller with vehicles, although more people are dying on the road than in the air or through airplane crashes. But with these ones, in automotive, you have several types of networks interconnected to each other, maybe 3-4 types of networks, and currently you have maybe hundreds of microcontrollers, and you have networks like CAN, Controller Area Network, that supports the cooperation of these microcontrollers. You may have other things like a local interconnect network that would control windows and so on. And then you have some things for infotainment. Nowadays, it's quite common to have something called FlexRay, which is a protocol that also supports both static and dynamic communication and so on. Now, this is the current picture, but the trend is towards increasing complexity and computation and communication needs. So here, if I take, for example, ADAS, and maybe there were some discussions about autonomy and ADAS in the past few days, you will have in the future a lot of more functionality. Already there's a lot of functionality in vehicles. Most of the innovation in vehicles is happening through cyber-physical systems and software in cyber-physical systems. And now even more functions are coming. Before, maybe you had hundreds of microcontrollers, for example. Now there's even more demand because you want adaptive cruise control. You want to have some warnings if you depart. For example, if you want to go to another lane, you want to avoid any collision, so it should warn you, and so on. Assist you in braking, and all of this is implemented nowadays into some driver assistant platforms that has maybe very powerful ECUs, several multi-core processors, several systems on chip, maybe supported by GPUs, graphic processing units, because you have a lot of video coming that you have to take decisions based on the incoming video streams and so on, and a lot of sensors, different types, maybe not only video but also things like LiDAR, for example, and so on. Besides the typical functionality that they have for powertrain, which is controlling the engine, and chassis, controlling the car, and so on. So there's more functions coming in. And then how do you, let's say, what kind of architectures do you need to be able to run all this complex functionality and exchange data? So I come back to that in a moment. But what we see is that in general, there are two separate directions with architectures in cyber-physical systems. One is focusing on critical applications and one on best effort applications. In critical applications, you look at something like avionics or automotive. What you want is especially safety. You want that you can provide guarantees that risks are reduced to an acceptable level. And for that, you use worst-case assumptions. You have a static reservation of resources. You have all sorts of tools to do analysis. And typically, the execution platforms are rather simple. But then it leads to what is called over-design or underutilization, that you need. Maybe you use the processor very little. There are not that many type of architectures that are developed for the mass market like this. There are processors that maybe you don't hear about, like Infineon, Aurix, tri-core processors that have 2 cores that are working in lockstep, for example. These are typical processors used for such architectures. But what everybody has heard are these type of best effort architectures, like your Intel processor inside your laptop, or some other kind of processing that goes on in a smartphone. These are what is called the best effort, where what you want is to make the average case fast, but then you cannot provide guarantees for the worst case. And the resources are reserved dynamically and so on. Architectures are quite sophisticated, you are adaptive and so on. But it may lead to temporary unavailability, which you cannot tolerate in critical architectures. And what is currently happening is that we are moving from federated architectures, like the one I showed you Here, so this is what is called a federated architecture. Each computer is a node, and you develop the computer based on its level of criticality, safety, integrity level. And we are moving from that to a case where such a federated architecture, where each application gets its own computer, and then you can guarantee safety, timeliness to an integrated architecture, because simply we're adding so much functionality that it's not possible to have one function in one computer. And now you have in integrated architecture, you have mixed criticality applications that share the same architecture. So applications that may be highly critical, for example, this one share the architecture with something which is not so critical. And this is also supported by the evolution to multi-cores that give you more processing. But this introduces a big problem, because now you have on the same platform hosting applications that are both highly critical and some are non-critical. And this is an issue how to support them. And I'll mention some of the challenges and the solutions to that. We're introducing new technologies like multicores. You've heard about multicores. It's basically instead of having a single computation unit on a processor, now on a chip, you bring multiple processing units on a chip, and then you have multicores. It may have its own network and so on. These are very important because there's a lot of companies developing these multicores. They give you a lot of what is called swap. They are smaller in size. They have a lower weight, a lower power consumption, more performance, for example. So everybody wants to use them. But how do you run a critical application on a multicore if the multicore is sharing the same application with a less critical application? And then the non-critical, less critical application may crash your highly critical application. How can you run here, for example, a flight control if here it's something that is disposing the, for example, toilet in an airplane? How do you separate those? Because people would like to put more applications of different criticalities in the same platform. So how do you provide a separation? Because with certification, and you heard yesterday about certification, certification actually requires that when several functions of different safety integrity levels that are a different integrity, if they share the same platform, multi-core, the standards tell you that the hardware and software has to develop the highest seal. So if I showed you this picture here, basically the standard says, okay, you want to share, that's fine, highly critical with non-critical, but then you have to develop everything, including the non-critical, as if it will be a highly critical application, because otherwise this non-critical application may crash the higher criticality application. This is extremely expensive. Certification introduces, maybe depending on the criticality level, increased costs, 10 times more costs to develop one line of software for a highly critical software compared to a non-critical software. And then with this integration, then certification becomes extremely costly unless this is what the standard says. So this is a quotation from the standard. You can show that the functions are, implementation of the safety functions is sufficiently independent. So how do you have this independence? And this is another thing with cyber-physical architectures, that they become partitioned. So you put a lot of things into, integrate into one multi-core, for example, but then the multi-core you have is no longer that you share everything with your applications. You virtually partition different resources in your multi-core and give them to different criticalities, different applications. And people talk both about spatial partitioning and temporal partitioning. With spatial partitioning, what you have is that you don't want, for example, a lower criticality application to corrupt the memory of a higher criticality application. So you have some ways of protecting the memory and protecting access to shared resources and so on. So it ensures that the software in one partition cannot change the software or private data in another partition. But then you also have what is called the temporal partitioning. That is not enough that you separate them from each other as if they would be, so this is conceptually as if they would be on separate computers, but it's on the same multi-core. You also have to ensure that activities in one partition do not disturb the timing and events in the other partition. And then this could be a potential solution that you do static scheduling, but it's not the only solution. And temporal separation is very difficult. You would like the highly critical application here to feel as if it has the processor all by itself. But of course, sometimes the lower criticality application also has to run. So how do you make sure that the lower criticality application does not disturb the higher criticality application? It's not only that, but even if you consider only critical applications and don't look at partitioning, you still have problems with multicores because of something called timing dependencies. I don't know how much you know about real-time computing. I guess there were some discussions in the past few days. With real-time systems, what you want is to provide some sort of guarantees that your execution of your functions would complete within a specified amount of time, for example, within a deadline. So let's look at an example. What if I have two real-time tasks? And here I'm looking at a multi-core ECU. The multi-core ECU has two cores. Core 1 that has some local resources, core 2 that has some other local resources, and then it has also some shared resources. This could be a shared memory, it could be a shared bus. So all multi-cores need to have some global resources, otherwise it's not a multi-core. It's like having several CPUs on a single die. And then what I'm looking at is an execution timeline. This is how the timeline is going from here to here. And I have these two tasks, task tau1 and task tau2, running and sharing one core. And what I have here is a critical section. Sometimes when tasks need to access a shared resource, they can only do that individually. So if you know a little bit of operating systems, you have learned about critical sections in programs. So during that red part, they cannot overlap. That's the idea. So if I run it, then it seems that this one finishes here and this one finishes here. Its execution, this one is a lower priority task. So when it comes here and wants to start, it will be interrupted by this higher priority task. Now, what happens if I add another task, tau3, on the other core, on core 2? So then the execution looks like this. Task tau3 would start executing and go into using the shared resource, this red part, which means that my task tau1, which was a higher priority task on this core 1, is not allowed to start yet to execute because it's you cannot use the shared resource at the same time. It's an exclusive use of the shared resource. So it would have to wait. So it waits until here, and only then it is allowed to execute. The same thing happens here. It may be again blocked by this task on core 2 from using the shared resource. And what happens ultimately that this will take much longer to execute compared to executing here. And the same with tau2 will take much longer to execute. So although I'm taking a lot of care to have a real-time application within deadlines, and I look at the worst case execution times and all that, just by having another core here that is using the shared resource, suddenly my timing is affected. So this is an example of two applications that are not temporally isolated, because this task here is influencing the behavior in timing from my other application. And I don't want that. And I don't want that just because I have a multi-core now, it's much more difficult to meet deadlines. So this was an example for a timing dependency. There's another problem in general with all sorts of new technologies like multi-cores. So you have increased response times. And this is the conclusion that the timing dependency introduces this problem for this separation. Maybe one observation that I would like to make is that, that we are talking about new processors, new communication technologies and everything. Which is perfect, and you have, you change your phone every second year or so. Maybe it's no longer every year because they became quite expensive, but every second year you change your phone, and then of course it has a new processor. Those processors for consumer electronics are typically designed to last for just a few years. But if you look at an airplane, they would be in operation for 30 to 40 years. If I take the processor from my mobile phone and put it in an airplane, what happens? Because these are designed with a shorter life cycle. they will fail after a while, because simply we want to have a lot of performance, but we want to have them as cheap as possible. So then what happens if you want to have them in operation for 40 years? It's the same in industrial automation. You have a robot or some other control, maybe the person that has been designing it and programming it has retired long time and has to go work for 40 years. You don't want to touch it. So it's a problem that with consumer electronics, maybe they have a 3 to 6 year production life. It's also about production. I put a multi-core, for example, the one from my mobile phone, I put it in an airplane. Will the company be around to give me a replacement if something goes wrong during service of this airplane for 40 years? Will I be able to buy it somewhere on the market? Actually, companies like Airbus stockpile Intel processors just because nobody's fabricating those anymore, and they want to be able to service an Airbus 340 that uses an 8286, for example. So that's another problem, and these areas that have these needs are called the space customer, because typically in a satellite you will have this problem, or in an airplane. But you have such needs also in other areas like industrial automation, and maybe less in vehicles, and even less so in consumer electronics. So this is also something to think about in terms of introducing new technologies in areas that are safety critical. Okay. Because of these architectures are distributed, the network plays a central role in their functionality. And in the past, and it influences a lot in terms of timing and reliability, safety, and so on. In the past, what you would have are specialized protocols in several areas. Maybe in a vehicle you would have something like CAN, controller area network, or FlexRay. In avionics, you would have something like SafeBus or AFDX. In industrial automation, you may have a Profinet or EtherCAT. Each area would have a specialized network that can support real-time and safety-critical functions. But the trend is towards integrating different types. So the similar integrating trend that you see in computation is also in networks. And right now, a lot of, because we have increasing complexity and we want to transfer more data, imagine all these video streams coming from autonomous moving objects like a vehicle or a robot or whatever, you cannot use this older type of networks for that. So what you want is something that is high speed but also low cost. And Ethernet is such a protocol if you talk about wired networks. Wireless networks is a different topic. You have now this trend towards 5G. People are also talking about using wireless for dependability, but my focus now is on wired networks. And Ethernet is a low-cost, high-speed wired network, but people have shown that it's unsuitable for real-time. You cannot bound the transmission times because of the collision mechanisms and how they are handled in Ethernet. But the trend is towards extended Ethernet to make it more dependable, make it, for example, be able to bound timing. So with Avionics, I told you about Avionics full duplex switched Ethernet, which is called AFDX, which is a standard ARINC 664/7. It's a standard and this is an implementation of the standard by Airbus. And you have EtherCAT, for example. But even more nowadays, people are working towards something called deterministic Ethernet, and to be standardized by IEEE, which is the standard called IEEE 802.1 time-sensitive networks. And this is supposed to be applied in many application areas. These are some application areas. And this is standard, so it will become de facto standard probably in many application areas, because it's solving a lot of problems that traditionally were solved by specialized protocols. So this is coming. A lot of the wired networks will be standardized on top of this time-sensitive networking protocol. That is because actually when you look at the wire, you can see is exactly like with partition architectures, you can see virtual cables going through the same wire, implementing different criticality protocols.
Is TSN focusing on wired? Does it also cover wireless?
There is an effort now to move TSN towards wireless, and there has been a working group established to look at that. How do you implement this in wireless? But I started with wired, and this wireless is some very new development, and it's not clear what will happen.
And we have a follow-up speaker, James Gross, touches on wireless. That will be a compliment.
And there is a very interesting development there. How do you make wireless more dependable? How do you make sure, because because with wireless you have the medium is not so stable as a wire, and then you have problems where you need to increase the power of transmission and retransmit and so on to achieve the same level of dependability that you have in wired communication. And I'm talking about cyber-physical systems architectures, let's say within one cyber-physical system, and within, let's say, a car or an airplane, you are still currently using wires. There are EU projects looking at how do you replace those wires with wireless, also within a vehicle or within an airplane. And of course, when they talk to each other, V2X, vehicle to vehicle, vehicle to infrastructure, and all that, it's on wireless protocols. But looking at single cyber-physical system unit, of course, they become systems of systems. But looking within a single unit is about wiring. And this is how it could look like in a car, that you have maybe multiple virtual machines or partitions within such a multi-core that may be supported by a system on chip and a hypervisor. Hypervisor is a virtualization technology that sits in between the hardware and your software functionality. And then these applications will have different criticalities and different needs. Some of them may have very demanding safety critical traffic and with very low latency, for example. And then you have, with TSN, you have something called time sensitive or synchronous traffic that can go at the same time, sharing the same wire with some other traffic which may not have such strict guarantees, like streaming traffic, audio, video, for example. It's called AVB in TSN. And then you have the standard Ethernet traffic that is best effort traffic. And the way this is implemented is through mechanisms within each network switch. So you would have a deterministic Ethernet switch here, and these are switched networks that actually can control when can lower priority traffic can go, and this is controlled via something called gate control lists that are opening and closing the access to the physical links by the different types of traffic. But this is now also what is happening in cyber-physical systems. And then in a vehicle, a network will look like this, that you still have your CAN networks, your FlexRay networks, and so on in a vehicle, but you will have probably increasingly, some of them will become deterministic Ethernet networks, mostly because, and this is something that you showed in your introductory slides. I saw this picture. I don't know how much you touched on it, but the idea is that you simply cannot handle the amount of traffic needed for ADAS functions, these are advanced driver assistance functions, and future autonomous functions. You cannot handle them on traditional networks like CAN or FlexRay, so you need more the high bandwidth networks like Ethernet, and especially if you are concerned about real time, then this is actually time sensitive networking. And then this would be used as a backbone network interconnecting several types of networks inside the vehicle or an airplane and so on. So this is how it could look like. Now, moving on, you also have a trend that is trying to converge something called operations technologies, which is a term from industrial automation, like controlling the robots, with IT. Why not move everything to the cloud? I would like all the controlling functionality of robots. I don't want boxes around robots. I just want a cable, and I want maybe a wireless box, and it should be controlled from the cloud. Why shouldn't I have that? And there is this trend where a lot of technologies are to be replaced by IT. People call it this convergence of IT, cloud, service-oriented architectures, and so on, to control these endpoints here at the edge of the network. And this is supported by a new computing paradigm, which is called fog computing. So with industrial, you can connect many things to the cloud. My mobile phone is connected to the cloud. Maybe your smart meter is connected to the cloud, but you cannot bring directly control a factory on some industrial processes from the cloud. So instead of moving everything to the cloud, what happens is that the cloud comes closer to the edge of the network. And a cloud that comes closer to the edge of the network or comes close to the ground, people call it the fog. So it's a cloud that is closer to the ground, is fog, sometimes also called edge computing. This fog computing is a new computation paradigm where you bring some of the properties of the cloud closer to the edge of the network. And this is implemented, for example, through some edge computing or fog computing nodes that distribute the resources, computing, storage, and control, and networking anywhere on this continuum from the cloud to the things which are the endpoints here. And to give you an example, in industrial automation, you would have this kind of hardware convergence. So you have all these systems. So this is a manufacturing cell with robots. Robots are controlled via all these boxes. You may have gateways, other things for networking and so on. What I would like to have is to get rid of all this equipment and instead install a single box, like it would be a miniature data center, but with hard real-time and safety-critical capabilities, because it's supposed to run the same safety-critical software. And then connect this also to the cloud, so I can do all sorts of analytics and so on. And this is happening now. A lot of this functionality in industrial automation is now converged and virtualized into such, to run on such fog computing nodes. And of course, this is coming to other areas, not only industrial automation. So the vision is that cars will become fog nodes on wheels. So a car now has such a tremendous computation needs that it will become a small data center on wheels, because it has to do machine learning, it has to do, get all this sensor data from all sorts of sensors, and needs a huge computation capabilities. This is achieved. You cannot put a data center here, but you can put something called a fog node, which integrates even more functions. And the fog node would provide the same level of dependability as the ECUs that are currently used for ADAS, for example. And of course, all of this has to be connected with other cars, has to be connected to the cloud. So you'll have a lot of mobile fog nodes in an intelligent transport system. Already companies like Cisco are deploying fog nodes in the infrastructure. So for example, a pole that is a traffic light already contains fog nodes, for example, from Cisco or from some other companies that is offering computation and communication capabilities closer to the edge of the network. So you may implement intelligent transport systems like traffic systems and so on. So this is what's going on with trends in architectures in terms of more Moore. We have more computation capabilities. We end up having a data center driving around in the town, basically. That's what's happening. But there's also another trend called more Moore. So more than Moore. So more Moore is going from cubes like this to multicores, right? But I'm also working on an area which is going from tubes like this to such chips. So you all know about biochemical analysis. You have to take a blood sample, maybe go to the doctor, run some tests. Nowadays, we actually can build chips for that. So the vision is, in terms of a trend, this mega trend of more Moore, that you go to the pharmacy, take something like this, prick your hand like you do it, for example, to do some glucose tests. Nowadays, we are a simple prick, put it next to your or inside your smartphone, and then you get the same type of blood test that you can do in a more complicated, let's say, a traditional biochemical lab. So these biochips are miniaturized biochemical laboratories, and these are becoming, let's say, additional sensors to cyber-physical systems that are able to monitor the environment for all sorts of threats, monitor air quality, water quality, maybe monitor your own health, for example. And there are many ways of implementing these. I have been working with some implementations, for example, that look like this, where you have valves that are controlling how fluid goes through channels. This is all through pumps that apply air pressure here to close and pinch a channel, for example. And then also by repeatedly pinching here the channel via some valves, you build what is called a peristaltic mixer. So you can mix liquid like this. And we can build this with a simple micro milling machine. Costs maybe $1,000, sits to on your desktop and can produce these things. And companies have integrated thousands, 20,000 such valves on a single chip. to something like this, also built in a DTU in the lab where I work. These are droplets which are moving on a chip, and you can mix them and transport them, heat them, and so on. And this is through something called electrowetting on dielectric, these are electrodes that actually the way you apply current. For example, to move it like this upwards, you would switch off an electrode, then switch on the next electrode, and through a physical principle called electrowetting on dielectric, it will move. And then you can do all these operations, and researchers are using this, for example, to support analysis, so to replace traditional biochemical labs that are currently used, for example, in synthetic biology to create new strands of DNA and so on. You can run something like this on a biochip, and it's currently used in large scale in the US, in those US states that mandate a lot of genetic testing for newborns to screen them for genetic diseases. And it turns out that such chips are a very cost-effective ways of screening for multiple genetic diseases, up to 24 genetic diseases. You can, from a very small droplet of blood, because you cannot draw too much blood from the newborns, and then you can find out if they have genetic diseases. And this is mandated by some laws in some US states. And finally, I have 2 more minutes. I show you a video. So this is the pretty picture that these biochips look very nice, but this lab on a chip, it's called lab on a chip. The lab on a chip, the reality is looks more like a chip in a lab, because you need a lot of cables to control those valves and those electrodes and so on. And what we are working on is to make some such control basically pneumatic. So this is a computer system that implements same gates, same everything, but works with air, not with electricity. So you simply have a pump like this. Maybe I can run that. Let me see. I can run that last video, and that's my last slide. Just to tell you that cyber physical systems is not just multicores and networks. If I can run this, where is my cursor? So what is happening is that I just create some vacuum with that syringe, and then suddenly this is just plastic with some flexible membrane starts to work. And this is I think it's just doing some computations here. And I can use this and put it on the chip itself, such that I don't need all the control apparatus around the chip. So the chip in a lab is more like a lab on a chip. And I can go with this to areas that may not have access to medical infrastructure, and simply with some setup like this, I can run all sorts of analysis. And I can use this as sensors in a larger cyber-physical system. So this was, I finished exactly on time, so 12:15, so we have time for lunch. But if there are questions, I can take them now or during the lunchtime.
So Paul is working on timing analysis, and he passed the test. Yes, there is time for a few questions. So now we have really deeper into the computing platforms, and we see the corresponding complexity, novel phenomena emerging. Maybe to follow up, from my side, Paul, you talked about the trends here. You didn't perhaps explicitly mention middleware. So, I mean, communication at different levels is just proliferating all over the place. And I think you touched upon OPC, AutoSAR. There are a couple of middleware technologies, but they also partly suffer from the fact that they deal mainly with logic and guaranteeing timing and so on. It's an open issue.
So indeed, now that you have so many functions on a single platform, they are not only integrated, but they are also distributed. So you may have here a control application on one multicore having to talk to another application on another multicore. How do you do that? And then different areas like automotive have an answer for that. In automotive, the answer is called AutoSAR, which basically aims at having independence between hardware and software. Their initial vision was that the same function I can move it to another ECU. But AutoSAR also gives you something called a runtime environment that is like a way for a task called a runnable to communicate with another function called a runnable on the same multicore or a different multicore. The problem is also that if your tasks are extremely critical, then something like the AUTOSAR may not be enough. So there are companies like TTTech, and you'll hear from the founder of TTTech, Herman Koppetz, tomorrow, that develop things like specialized middlewares like MotionWise that is using static scheduling of communication and so on. But exactly, so what do you have in between your software here such to enable seamless communication with other software somewhere else? And especially because you may have virtualized resources, one operating system running here, maybe another operating system running here, running on different virtual machines which are enabled by type 1 hypervisors that sit in between the hardware and your operating system, and having to use a backbone like deterministic Ethernet. It's a nightmare if you want to develop an application to talk to another application and maybe talk to the cloud. So what is the right abstraction and how do we implement such a middleware that goes beyond what the typical operating system offers you and enables such a communication that has to be real-time as well and has to be dependable as well. So that's a good point which I didn't touch. Yes.
So any further questions?
Yes?
For the need of communication, you said like real-time need. I mean, we saw that those wired protocols, and you mentioned like in the car that cars have to be connected and to infrastructure. Is there a wireless protocol out there right now, or maybe 5G meets that in the future, that you have like that real-time capability?
There are a lot of wireless protocols, and we had just completed an EU project called SafeCop on how cyber-physical systems cooperate using wireless, especially if you want to rely on wireless for safety functions. Because at the moment there are wireless protocols. I mean, Wi-Fi, you can get the cars to talk to that via that to each other and to the infrastructure. The question is, do you want to rely on that to implement? For example, if you look at vehicle platooning, can you trust the truck in front of you? You are in a platoon. I don't know if this has been discussed. Platooning is like a road train of vehicles. And you have a truck in front of you that is telling you via wireless, brake now, emergency brake now. Can you trust that message? Does it arrive in time to actually for you to brake and not have a collision? And it turns out that there are multiple issues here. One is with latency. Can you do this fast enough? In what conditions? The other one relates to the overall concept of dependability. Can you trust the integrity of that message? Can you trust that it's the truck that is telling you to brake now and not somebody else, so let's say, pretending to be the truck takes you to brake now? And then in that project, we looked at off-the-shelf protocols. I'm not an expert on wireless. Is this 1011? What are these some Wi-Fi protocols that will be talked about by the next speaker? Yeah. But even COTS protocols, you have to build a layer on top of them, a safety layer on top of them, and you consider them a black channel. You don't trust them. Mm-hmm. And then you have some application functionality on top that actually just considers that you have a black channel and then encrypts all communication and then decrypts communication, maybe has to resend some messages. Let's see how much James will cover. Otherwise, it's a very good question for him too.
I think since we are transitioning now, we should be having jointly lunch, and we will be back and start again 1:15. And I think we can open the doors here, right? So